Hello everyone and welcome to another lesson. In this video, we will be discussing the process of performing a material balance. After watching this video, it is expected that you will be able to describe the relationships between the inputs and outputs of single unit processes. Let's begin. In its most basic definition, we say that a material balance is a direct application of the law of conservation of mass to the design of processes. It's like we are applying the law of conservation of mass to a specific process. At steady state, we say that this is characterized as mass input is equal to mass output. Majority of the problems that we will be solving are steady states problems. The definition of steady states will be discussed later. In general, we say that the law of conservation of mass is stated as mass can neither be created nor destroyed in any physical or chemical process. Mathematically speaking, we can represent it with this general balance equation. That is mass input plus mass generated minus mass output minus mass consumed is equal to the accumulation of mass. This general material balance equation can be simplified depending on the type of the process. Throughout our analysis of the material balance process, we will be dividing our systems into two categories. Those are reactive systems and non-reactive systems. 2 out of 5 terms in our general mass balance equation pertains to reactive processes only. We have generation and consumption. Generation and consumption are determined by stoichiometry, and they are exclusive with reactive systems. Accumulation is another special term in our mass balance equation in such a way that it is present whenever there is an imbalance between the inputs and the output. For now, we will be sticking with non-reactive processes without accumulation. Those are non-reactive steady state process. And with that, we have to discuss what are the different types of processes. The type of process or our assumption on the processes will have an impact on how do we proceed with our material balance equation. You can generally classify processes into 3 types. Those are the batch process, which we also call transient process, the continuous or steady state processes. These are majority of our examples. And we also have semi-batch or fed batch processes. The semi-batch process is a hybrid between the batch and the continuous process. For now, let's focus on the simpler continuous processes. For the continuous processes in which there is no chemical reaction, we can remove the terms of generation, accumulation, and consumption in our general material balance. Therefore, for a continuous process, we can simplify that by writing in is equal to out. This is our primary equation that we will be applying to almost all of our examples. Basically, when you say that a process is steady states and there is no chemical reaction, then you can use this very simple mass balance. The input is equal to output equation can be applied to streams, and it can also be applied to components of streams. And we will illustrate that with our many examples showing how the material balance process is carried out. Let us first establish the basics. The basics of how to make or how to perform a material balance. We will be following the 5 steps enumerated here, but we will do this with an example so that you can follow along. Let's consider this example. An aqueous solution of sodium hydroxide contains 20% sodium hydroxide. It is desired to produce an 8% sodium hydroxide solution by diluting a stream of the 20% solution with a stream of pure water. Determine the feed rates of the 20% solution and diluting water needed to produce 2,310 pounds mass per minute of the 8% solution. Let's first have number 1. Identify the process, process unit, and process streams. Identifying the type of process and the type of process unit would greatly help us in determining what type of solution will we pursue with these types of problems. First, what is the process? From our understanding of the problem, we are taking one stream, that is the 20% sodium hydroxide solution, and we want to generate an 8% sodium hydroxide solution. Basically, we want to dilute the 20% solution by adding water. By doing so, what we are doing is a mixing process. So, in short, the process in this case is mixing. Basically, we are mixing 2 different streams in order to come up with one stream. And we want to come up with an 8% sodium hydroxide solution. So let's write here, the process is mixing. Next, let's identify what is our process unit. If you will remember, the process unit is an apparatus or equipment that is used to carry out the process. So what equipment do you need if the process is mixing? The answer is you need a mixer. So therefore, the process unit is a mixer. Finally, we identify what are our process streams. The process streams are the inputs and outputs for the system. The first process stream is the 20% sodium hydroxide solution. This is process stream number 1, and let's classify if it's an input or an output. From our understanding, this is an input to the process. What is our next process stream? From the wording of the problem, it is desired to produce an 8% sodium hydroxide solution. So the 8% sodium hydroxide solution is our process stream number 2, and this is considered as an output because we want to produce this stream coming from an input, which is the 20% sodium hydroxide solution. Okay? Now, what do we need to mix with the 20% sodium hydroxide solution in order to lower its concentration? Of course, we will be mixing water, and that is another process stream. We want to produce the 8% sodium hydroxide solution by diluting a stream of the 20% solution, which is one of our inputs, with a stream of pure water. Water is our process stream number 3, and this is considered as another input. So by dissecting the problem, we have determined that the process is mixing, the process units is a mixer, and we have 3 process streams. We have 2 input streams and 1 output stream. We are done with step number 1. With the information gathered from step number 1, we then proceed to step number 2. Draw and label the process using block diagrams. Label the given values with correct units. Also, do not forget to properly place your inputs and outputs. Inputs are arrows going toward the process unit, and outputs are arrows going away from the process unit. Here's the same example, and let's attempt to draw our flowchart to represent the system with the knowledge we obtained from step number 1. We know that the process unit is a mixer, so let's draw a box. Let's label this as our mixer. And let's represent our process streams. We determined that we have 2 input streams. Our first stream is the 20% sodium hydroxide solution. I will call this stream A. And let us write what do we know about stream A. Well, first, we know that stream A is an aqueous solution. It's an aqueous mixture that is composed of 20% sodium hydroxide. And presumably, the remaining 80% is water because this is an aqueous solution, meaning it has to contain water. Okay? So that is our first process stream. What is our second process stream? Let us recall what is our second input. In order for us to lower the concentration of stream A, we need to mix it with stream B, which is pure water. This is the diluent in this case. Okay? Remember that in the previous step, we identified 2 inputs and 1 output. So we are done with the 2 inputs. Let us now characterize our output. Our output is what we want to produce. We want to produce an 8% sodium hydroxide solution. Then that should be our output stream. I will call the output stream as C. And stream C contains 8% sodium hydroxide, and presumably, the remaining 92% is water because we only have 2 components in this problem, the sodium hydroxide and the water. This is the diagram that represents the problem. It is from this diagram that we will be basing all of our remaining solution. So it's very important that you get this part correct. You need to make sure that all of the given in the problem is represented properly in your diagram. If you cannot properly draw a diagram, then it would be questionable whether you can answer the rest of the problem. Okay? So representing the problem in a diagram is the most important step in the material balance process. Now let's browse through the rest of the problem and see what other information can we get that would be helpful in solving the problem. We are done with the compositions of the stream. So we have stream A, stream B, and stream C all having their compositions. But there is another given in the problem that is 2,310 pounds mass per minute of the 8% solution. This parameter is a mass flow rate because of the units pound mass per minute. And this mass flow rate pertains to the flow of the product. It was specified that it is for the 8% solution. So we say here that our stream C has a mass flow rate of 2310 pound mass per minute. And that is our complete diagram. Always make sure that your entire problem is represented in the diagram. Now let's proceed to step number 3. Step number 3 is select a basis. We have talked about selecting a basis in our previous lesson, and in this case, you may want to select a basis that would benefit your problem-solving approach. For example, if you are given a flow rate, be that may a mass flow rate, volumetric flow rate, or molar flow rate, a very sensible basis is to assume whatever's the denominator units of that flow rate. For example, if you are given 2310 pounds mass per minute, one of our best bases could be we just assume that we have 1 minute of operation or 1 minute of mixing, right? Because if you assume that your basis is 1 minute, then you already have the mass of stream C, that is 2,310 pounds mass. In fact, that is what we are going to do. We say that our basis is 1 minute of operation. This basis allows us to have the simplest material balance solution. You can assume any other value aside from 1 minute. Let's say, for example, that your basis is 1 hour of operation. You can also do that, but then there would be a couple of other extra steps that you need to do in order to adjust your given to your chosen basis. So choose the simplest basis whenever possible. And that's step 3. Let's proceed to step 4. Select your system boundaries and perform material balances starting with the overall material balance, then follow with the individual balances of the components. So let's do that piece by piece. What is a boundary? A boundary is simply a dotted line that we draw around certain systems in which we are considering what streams are going in and what streams are going out of my system boundary. For processes with only a single unit, you are left with no choice but to select your unit as your boundary. So for clarification, let me draw the boundary here. I say that we are setting the boundary around the mixer. In our future lessons, when we will consider processes with several unit processes, then we have to specify our boundaries. Okay? But for now, it is enough to say that for a single unit, your boundary is around that unit. Before proceeding with the balances, let's first determine what is required from this problem or what is being asked from the problem. The problem statement is given here. Determine the feed rates of the 20% solution and diluting water needed to produce 2,310 pounds mass per minute of the 8% solution. Our required in this case is A and B. Remember that A represents the flow rate of the 20% sodium hydroxide solution, while B represents the flow rate of the pure water stream. And we just want to determine their feed rates or simply the flow rates in which they are going into the mixer. Now let's perform the OMB. OMB stands for an overall material balance or overall mass balance. This OMB is a simple equation that simply states input is equal to output. That is our law of conservation of mass for non-reactive steady-state processes. So let's just determine what streams are going in and what streams are going out, and they should be equal. For our problem here, we have two streams going in, that's stream A and stream B. So we say that A plus B, this is the summation of your input streams, and this is equal to the summation of your output streams. We only have one output stream, so we can say that A and B is equal to C. And that is your OMB, or that is your overall material balance. It's that simple. At this point, you can now substitute whatever values are given for either A, B, or C. We are given the flow rate of stream C, so we can substitute that as A plus B is equal to 2310. We just have to remember that all of the terms in this overall material balance are in pound units. If you will notice, this equation contains two unknowns, that's A and B. And we cannot solve an equation with two unknowns unless we find another equation with the same unknowns. And we will get our second unknown with what we call the component balances. For the component balances, you will take a look at a particular component of the system. Let's define what is a component. A component is a substance that can be defined separately for our problem. In our example here, we only have two components. The first component is sodium hydroxide. And the second component is water. If you take a look at the systems, stream A contains two components, NaOH and water. Stream C also contains two components, NaOH and water. But stream B only contains one component, that's water, because stream B does not contain any sodium hydroxide. So we say that for the entire system, we have two components, and therefore, you have the capability to perform two component balances, one for sodium hydroxide and the other for water. But in this case, we only need one of the component balances because we already have our equation number 1, which is our overall material balance. So let me illustrate our sodium hydroxide balance. For the component balances, you will still be applying the law of conservation of mass, that's input is equal to output, for non-reactive steady-state systems, but we only have to focus on that particular component. Our mass balance in this case, I will write it as NaOH in is equal to NaOH out. We are simply saying, since there is no chemical reaction and there is no accumulation, that whatever sodium hydroxide comes in, it must also be the sodium hydroxide that comes out, right? And we just have to figure out how to mathematically represent that. So let's write our equation for the sodium hydroxide balance. For our sodium hydroxide in, we can have two sources, stream A and stream B. However, we know that stream B does not contain any sodium hydroxide because it's pure water. So we will not be including that in our balance. Okay? Stream A contains 20% sodium hydroxide. We are assuming that this is 20% by mass because this is a liquid system. How do we mathematically write that? Well, we write the amount of sodium hydroxide coming in as 0.2 times A. 0.2 is the mass fraction of sodium hydroxide in stream A, and letter A represents the total mass flow rate of stream A. So when you multiply the total mass flow rate with the mass fraction of the component, you would get the mass of the component. So we say that this is the mass of sodium hydroxide in stream A. To complete our material balance, on the other side of the equation, we represent the mass of sodium hydroxide coming out of the system. And that is represented by our single output, which is stream C. In stream C, we have 8% sodium hydroxide. So we write that as 0.08 times C. 0.08 is the mass fraction of sodium hydroxide, and C represents the total mass flow rate of the output stream. Now, if you take a look at this equation, we don't know what's the value of A, but we do know the value of C, so we can substitute. We write 0.2A is equal to 0.08 times the value of C, 2,310 pounds mass. We are using mass units only instead of mass flow rate units because of our basis 1-minute operation. Solving this equation, we can look for the value of A. Substituting, that is 2310 times 0.08 divided by 0.2. This is the mass of stream A, 924 pounds mass. Since our basis is 1-minute operation, you can also say that the mass flow rate of stream A is 924 pound mass per minute. Now that we have the mass of stream A, we can substitute this back to our overall material balance or OMB in order to determine the value of stream B. Rearranging our OMB, we have the equation B is equal to C minus A. And we calculate that as 2310 minus 294. Stream B has a mass of 1386 pounds mass. In terms of flow rate, we can write that as 1386 pounds mass per minute. And just like that, we were able to determine the feed rates of streams A and B. Our interpretation of this solution is, if you want to obtain 2,310 pound mass per minute of an 8% sodium hydroxide solution, you need to mix 924 pound mass per minute of a 20% sodium hydroxide solution with 1,386 pound mass per minute of pure water. Okay? That is our interpretation. And that's how you perform a material balance. At the end of the day, this all boils down on how well can you interpret a problem. So you have to practice your reading comprehension skills because that factors a lot in understanding what the worded problem is trying to tell us. Remember that your representation of the problem is based on your understanding of the problem, and your final answer is based on the material balance, which is based on your interpretation of the problem. So if you cannot understand the problem, you cannot draw a proper diagram, you cannot perform a proper material balance, you would arrive with the wrong answer. The key for mastering this skill is constant practice. You have to solve as many problems as you can in order for you to get acquainted with the process of material balances. Now that we know the process, let's try another example. The oxygen in air is usually sufficient to sustain combustion, but it can be enriched to make combustion more efficient. In a certain process, it is required to produce a 50-50 mixture of oxygen and nitrogen by mixing air and pure industrial oxygen. How much in kilomoles per day of the 50-50 mixture can be produced from 250 cubic meters per day of pure oxygen at STP? STP stands for standard temperature and pressure, that is 0 degrees Celsius and 1 atmosphere. Since we are dealing with gases in this problem, we are going to assume that the given 50-50 mixture pertains to 50 mole percent oxygen and 50 mole percent nitrogen. Let's perform our step-by-step process. First one is identify the process unit, and the process streams. The process in this case, again, is mixing because we want to produce an enriched version of air in which you will be mixing air and pure oxygen. Since the process is mixing, we know that the process unit is a mixer. And we also know what are the process streams. The 50-50 mixture is a process stream, air is a process stream, and pure oxygen is another process stream. Now that we have that knowledge, let us represent the problem in a diagram. Our process unit is a mixer. And based on the problem, we have 3 process streams. We have 2 input streams and 1 output stream. For this problem, let us name the input streams as F1 and F2. And let's name the product as P. For the drawing of the diagram, you are not limited on how you want to represent your input and output streams. You can use whatever variables you want to use. I will call stream F1 as our air stream, and air typically contains 79% nitrogen gas and 21% oxygen gas. Stream F2 is our pure oxygen stream. This is 100% oxygen. And our product stream is what we want to achieve. We want to produce a 50-50 mixture of oxygen and nitrogen. That is 50% nitrogen and 50% oxygen. Another given in this problem is we want to use 250 cubic meters per day of pure oxygen at STP. So in our F2, we have here 250 cubic meters per day at STP. That is a volumetric flow rate, and we may want to convert that to a molar flow rate to suit our material balance problem. In this problem, our unit is not in mass, it is in moles because we are dealing with gases. For non-reactive processes, the mole balance is the same as the mass balance. The number of moles coming in is equal to the number of moles coming out. Just make sure to understand that this only works for non-reactive process. When we go to the reactive processes, you cannot perform the OMB as a mole balance. In this problem, we are required to solve what is the molar flow rate of the product stream, particularly in kilomoles per day, or the given feed rate of stream F2. Now that we have illustrated our problem, let's proceed to step 3, which is choose your basis. As I have mentioned, if you are given a flow rate, be that may mass, volumetric, or molar flow rate, you can use the denominator unit of the flow rate as the basis. In this case, we are given 250 cubic meters per day of stream F2. The denominator unit is day. Therefore, a sensible basis is we use 1 day of operation. By the application of our basis, it is our understanding that stream F2 now has a volume of 250 cubic meters, and this is pure oxygen. Before we proceed to the material balance, we have to convert everything to either mole or mass units. 250 cubic meters is a molar unit. You cannot use that in the overall mole balance because it's a volume, right? So we have to convert from volume to moles. And since this is a gas, we can assume that oxygen behaves ideally, and we can use the ideal gas equation. So we want to convert from volume to mole. We use the ideal gas equation, PV is equal to nRT. We solve for the number of volume of oxygen. This becomes PV over RT. Remember that we are using STP conditions, that is 0 degrees Celsius and 1 atmosphere of pressure. Let's substitute to solve for the number of moles of oxygen. Pressure, that's 101,325 pascals, multiplied by volume, 250 cubic meters, divided by the universal gas constant R in standard SI units, that's 8.314 Pascal cubic meters per mole per Kelvin. And we multiply that by the absolute temperature, 0 degrees Celsius, that's 273.15 Kelvin. The number of moles of oxygen is 11,154.38 moles O2. Or in kilomoles, this becomes 11.15. This is basically the value of stream 2. And we can use this with our material balance. Our OMB, or overall material balance, in this case, it also pertains to overall mole balance, is now input, F1 plus F2 is equal to output, that's P. Substituting what is already known, we have F1 plus 11.15 is equal to P. Always remember that these are in kilomole units. Since we have two unknowns, F1 and P, we have to look for other equations to describe the system in order for us to solve the unknowns. After the OMB, we proceed to the component balance. Let me take this opportunity to discuss what we call the tie component. The tie component, if present, is what allows us to simplify our material balances for a particular problem. The tie component is defined as a component that only enters through one stream and only exits through one stream. Let us examine our components and take a look if they satisfy the definition of the tie component. Based on our problem, we only have two components, oxygen and nitrogen. Let's take a look at oxygen. Oxygen enters at F1 and at F2 and exits at P. It enters at two streams and exits at one stream. Therefore, oxygen is not a tie component. A tie component can only enter and exit on one stream each. Let's take a look at nitrogen. Nitrogen enters at F1 and nitrogen exits at P. It enters at one stream and exits at one stream. Therefore, nitrogen is a tie component. Our tie component balance is 0.79 of F1 is equal to 0.5 of P. This means that stream F1 contains 79% nitrogen and the stream P contains 50% nitrogen gas. There is no nitrogen in stream F2, so that does not appear in our nitrogen balance. Rearranging this equation, this becomes F1 is equal to 0.5 over 0.79 times P. I'll call this equation 2, and we can substitute equation 2 from our OMB. Our OMB will become 0.5 over 0.79 times P plus 11.15 is equal to P. This equation now has only one unknown, and that is the product P. From here, we can rearrange the equation and solve for the value of P. Rearranging, this becomes negative 11.15 divided by 0.5 over 0.79 minus 1. P is 30.37 kilomoles. Since our basis is 1 day of operation, we can say that the flow rate of our product is 30.37 kilomoles per day. That is our final answer. The problem only asks for the molar flow rate of the product, but if you want, you can also determine the molar flow rate of stream F1, which is one of our feed streams. You can use equation number 2, that is 0.5 divided by 0.79 divided by P, 30.37. F1 is 19.22 kilomoles per day. You can also verify from our overall material balance if the values you obtained are mathematically sensible. For example, one way of checking if you are correct is you simply add F1 and F2 and their value should be equal to P. So we have the value of F1, 19.22, and to this we add F2, which is 11.15. This should be equal to 30.37, which is the value of our product. We can say that our calculations are correct. By now, you are getting a feel on how material balance problems are tackled or how they are processed. Just follow our 5 steps and you will be okay. Let's solve another example. An experiment on the growth rate of certain organism requires an environment of humid air enriched in oxygen. 3 input streams are fed into an evaporation chamber to produce an output stream with the desired composition. We have our 3 streams here. Stream A is liquid water fed at a rate of 20 cubic centimeters per minute. Stream B is air, composed of 21% oxygen and 79% nitrogen. Stream C is pure oxygen with a molar flow rate 1/5 of the molar flow rate of stream B. The output gas is analyzed and is found to contain 1.5 mole% water. Draw and label the flowchart of the process and calculate all unknown stream variables. So let us apply our material balance steps on this problem. First step is to identify what is the process. The process is essentially mixing, but it was specified that our unit in this case is an evaporation chamber. It just so happens that one of our streams is liquid water and we want to convert liquid water to water vapor because that is the specification of the problem. So the process is mixing with a little bit extra, and that is including the evaporation. Our process unit is an evaporation chamber. Let us draw our diagram for this problem. So we have our evaporation chamber, let's call that EC, and we have our 3 input streams. Those are A, B, and C. For our product stream, I will be calling that a stream P. And we are given the compositions of our input streams. Stream A is pure water, that's 100% H2O, with a liquid volumetric flow rate of 20 cubic centimeters per minute. Stream B is air, so that is composed of 79% nitrogen and 21% oxygen. Stream C is pure oxygen, and it was stated that the molar flow rate of stream C is 1/5 the molar flow rate of stream B. We write that relationship as C is equal to 1/5 of B. And before we proceed, let us analyze the composition of stream P or the product stream. We know that stream P is simply a combination of the 3 input streams. And our 3 input streams states that we have 3 components. Those are water, oxygen, and nitrogen. From the problem, it was stated that the output gas is analyzed to contain 1.5 mole% water. So we know that this is 1.5%. And for our required, we are asked to solve for all unknown stream variables. Those are the flow rates of A, B, and C. Before proceeding to the material balance part, let us first agree to use either mole or mass balances. In this case, since we are dealing with gases and since we are given a mole%, it would be easier for us to perform mole balances. So everything must be represented as either molar flow rates or mole%. With that, we have to convert our stream A, which is represented as a volumetric flow rate, that's 20 cubic centimeters per minute. So let's convert 20 cubic centimeters per minute to moles per minute, which is a molar flow rate. To do that, we have to convert from volume to mass and then from mass to mole. From volume to mass, we'll use density. From mass to mole, we'll use molecular weight. We are using liquid water and its density is 1 gram per cubic centimeter, so that is our first factor. For every 1 cubic centimeter, it weighs 1 gram. And then finally, for the conversion to moles, we say that for every 18 grams of water, that is equivalent to 1 mole of water. That is the molecular weight of water. Take a look at the cancellation of units. Cubic centimeter would cancel, grams would cancel, and you will be left with the unit mole in the numerator, and in the denominator, it's minutes. This is the molar flow rate of water. Calculating, that is 20 divided by 18. That's 1.11 moles per minute. We can now write that here, stream A is 1.11 mole per minute. This is the value that we're going to use for our material balances. Let's begin with the material balance proper. Let us set our basis. Our basis in this case is 1 minute operation because our flow rate is given as moles per minute. Our overall material balance, in this case, this is a mole balance, is A plus B plus C is equal to P. The summation of our inputs is equal to the summation of our outputs. We know the value of A, so we can substitute that. This becomes 1.11 plus B plus C is equal to P. We call this equation 1. Now, for our component balance, let's identify if we have a tie component, and that would simplify our solution. If you take a look at water, it enters at stream A only and exits at stream P only. So water is a tie component. Let's have the water balance. This is 1.11 moles coming from stream A is equal to 0.015 times P. That's because stream P contains 1.5 mole percent water. From this tie component balance, you can see that we are already able to solve for P. That's simply 1.11 divided by 0.015. The value of P is 74.07 moles. Now that we have the value of P, you can write our overall material balance, or OMB, as 1.11 plus B plus C is equal to 74.07. How can we solve for the values of B and C? Remember that we have a relationship for B and C. We say that the flow rate of C is equal to 1/5 of B. We can substitute that to our overall material balance. This becomes 1.11 plus B plus C is equal to 1/5 of B, and that's equal to 74.07. Rearranging and substituting, we are able to solve for B as 74.07 minus 1.11 transposed from the other side of the equation divided by 1.2. That is 1 plus 1/5. The flow rate of B is 60.8 moles per minute because our basis is 1 minute. And from this, we can solve for the flow rate of C because we know that C is equal to 1/5 of B. So we simply divide B by 5. The flow rate of C is 12.16 moles per minute. And that's it. We were able to look for the flow rates of B and C, two of our missing inputs, plus the flow rate of our product P. If you look back at our diagram, we were able to solve for the flow rate of B, and the flow rate of C, and the flow rate of P. However, we are still missing the composition of P, and that is, what are the mole fractions of oxygen and nitrogen in our product stream? That's also important, so let's try to solve for that. For that, let us represent the mole fraction of oxygen in stream P as the variable X. And for nitrogen, I can represent that as variable Y because we are simply representing with variables. However, a more sensible approach to representing the mole fraction of nitrogen in P would be 1 minus X minus 0.015. We are simply exploiting the fact that the summation of the mole fractions of all the components in P is equal to 1. So let's solve for the value of X. To determine the value of X, we simply perform another component balance. If you remember, we are done with the overall material balance, and we have also used the water balance. Let's now use the oxygen balance. The oxygen balance is, there is no oxygen in A, so we will not include that. In stream B, that is 21% oxygen, so we write that as 0.21 B. And then from stream C, that's pure oxygen, so we simply write C. And finally, on the product stream, we don't know the mass fraction of oxygen, so we write that as X multiplied by P. X is the mole fraction of oxygen in stream P, and P is the total molar flow rate of the stream. We already know the values of B, C, and P. We simply substitute those and we can solve for the value of X. Substituting, that is 0.21 times B, 60.8, plus C, 12.16, and the result is divided by P, 74.07. The mole fraction of oxygen, or X, is 0.3365, or this is also 33.65% oxygen. And of course, since you now know the value of X, you can solve for the percentage of nitrogen. That's simply 1 minus X, 0.3365, minus 0.015. This is the mole fraction of water in stream P. Nitrogen has a mole fraction of 0.6485, or that is 64.85% nitrogen. And with that, we have also solved for the composition of stream P. And that's the nature of material balances. You just have to exploit every possible material balance you can form. That is, first, the overall material balance, and then after that, you can perform individual component balances. After this lesson, you will be given more examples detailing the proper material balance solution for different types of process units. Certain process units have particular modes of solution, and it's important that we discuss all of them. But for now, this is the end of this video. I hope you learned something. Thank you for listening, and as always, keep safe.